Last class we were discussing about logistic regression. So today we'll complete logistic regression, and so we are majorly we're discussing about binary logistic regression. So we'll complete with multi-class logistic regression. Next, we started discussion about majorly logistic regression. So logistic regression, it is a regression by name, but it's a classification by task, right? So why it is a regression? By now we might have already thought of, right? So what we are doing, we are getting this same feature transformation we are doing W transpose X as we did in the linear regression, but we are getting the probability using this sigmoid function, right? So what is the sigmoid function? As we discussed, in linear regression, our output range is from minus infinity to plus infinity. But with that output range, we cannot always make decision, or we cannot run the optimization problem that will be very like kind of stable and optimal to do the classification task. So for classification, we need a 0, 1 decision or 0, 1, 2, 3, 4 decision, right? So how do we make that decision? So for that, we wanted to squeeze this minus infinity to infinity to 0 to 1, right? So then we can make decision, okay, if the whatever the value is, whatever value we are getting on the output side, if it is beyond 0.5 or beyond some threshold, that will belong to one class. Then if it is less than that threshold, then it will belong to other class. So that decision we wanted to make. That's why we kind of try to squeeze into a kind of probability distribution. So and then we thought of like which function can give us that functional like flexibility. Like sigmoid is like kind of straight away. Like if you convert apply sigma to like kind of a range of value between minus infinity to infinity, it will give us value between 0 to 1, right? So now it is a probability distribution. So that's why the like naming like adopted the regression term, because we're not directly, the model is not directly predicting the class level 0 or 1, right? It is predicting some probability value that is a kind of a regression value, so some floating point number. So that's why the name regression is there. But based on this probability value, we'll make some decision whether it is belonging to class 1 or class 0, right? So this is what the sigmoid does. Now we wanted to do the MLE, right? So if we do MLE, so what we have to do, we have to kind of maximize the kind of log likelihood. What is the likelihood of the data? So this is like a probability of xy given parameter theta, right? So if like kind of this is the probability of the complete data, but what will be our likelihood? What's the likelihood we want to achieve? The likelihood of the predicting correct class level, right? Correct y values, right? So that's what we want to achieve, right? So we somehow have to convert this probability of xy, this joint distribution of xy into to some distribution of y given x, right? So we started with the probability of complete data distribution, sorry, distribution of complete data x and y. Our target is we need to reach somewhere like y given x, right? Theta is anywhere there always, right? So how can we reach that? Okay, so you know the base theorem. How can you break down this into like kind of conditional probability? But yeah, let's see what are the exact steps. So this is the total data distribution. Now, if you multiply p of theta x on numerator and denominator, so it will not change anything to this formulation. Now, what you do? So you combine these two terms. These two terms you combine, right? So that will give us this probability of y given theta x, theta comma x comma theta or theta comma x. Now these two terms, this term and this term, that will give us probability of x given theta, right? Yesterday also during map we discussed as x is already given to us, so we don't need to like kind of compute the distribution of x given theta. So this is insignificant. So once you kind of open this expectation, this will be a constant term. So we can ignore this. So we have to focus on only this term, right? So now our like kind of maximum likelihood formulation boils down to whatever we wanted, right? Just probability of y given x theta, right? Then I know, so we know key all these data points are IID, so they are sampled from IID. One more thing, if you see like why we're able, so this was an expectation over this x-ray data, right? So we're able to kind of convert this into summation of summation of those IID values and kind of divide by number of instances. How are we able to do it? So the expectation is computed over the true distribution of xy. It's computed over true distribution of xy, but true distribution of xy is never given to us. Even if in the real world we never know the true distribution of the xy, we only know the sample distribution of the xy. So whatever data, let's say even if it's 1 million data points, this is a sample data point, right? So we always try to kind of estimate the parameter or maximize the likelihood of the parameter estimation using the sample distribution, right? This is called sample distribution. So, so that's why we directly don't apply the expectation. We kind of approximate that expectation to this formulation, like 1 by n into summation of all this, whatever the logarithm term, right? So we never in real world use the true distribution in any kind of machine learning setup, right? Always it is kind of sample distribution, and that's why many times you will see how do we like can convert a true distribution into sample distribution using either in the continuous case or in the discrete case using discrete case using summation, continuous case using integration, right? Now this is our kind of ML setup for the logistic regression. So now we have to kind of maximize this and get the theta. So let's see how do we do. We decided to get the kind of output probability, we'll use the Bernoulli distribution, right? So if our underlying distribution is Bernoulli for this formulation, so what is the kind of PM of Bernoulli? So we know if it occurs, let's say class 1 occurs YI times, it is and occurring of like, so what is Bernoulli? Bernoulli of P is like kind of it's yeah. So let me rewrite this. Bernoulli of x, let's say random variable is x. So what we'll say, it is p with if x equal to 1, it is 1 minus p if x equal to 0, right? So this is Bernoulli, the PMF of Bernoulli, you know. So if we convert into like kind of, so if you compute the PMF the Bernoulli, it will be like how many times the class level 1 occurred, let's say that occurred yi times, it is p to the power yi, and let's say class 0 occurred some xi times, it is 1 minus p to the power xi. This is the PMF of Bernoulli we know. So same thing we're applying here. So what are the class levels we have? We have only 1 or 0, right? These are the class levels. So yi belongs to 1 or 0. So if one class we are representing by class 1, other class we can represent by 1 minus class, whatever y1, yi. Right? So that's why we are able to write like this. We know for class 1 it is pi, for class 0 it is 1 minus pi, or you can make this into like kind of in multi-class case like some other class value. So that we'll see how do we convert it into multi-class case. Right? In binary case, we know for one class it is pi, other class it is 1 minus pi, then PMF will be the pi to the power yi, and then 1 minus pi to the power yi. And we want to maximize this, meaning we have to kind of compute the derivative and equate to 0, right? So, so whether you want to maximize or you can do what we can do also minimize the negative of that, right? So now if you apply a kind of log to it, log will expand to this part. Now you take the derivative and try to find the value of PA. Right. So that's what we'll do in the like kind of the gradient descent step. Right. So what are gradient descent of general formulation of the gradient descent? So you want to predict the parameter of at t plus 1 time step. So you have the parameter at t time step. You take the kind of derivative of whatever the loss at t time step with respect to the parameter. Right. So if we want to break down this kind of this nabla L, so this is called nabla parameter. So nabla WL. So this is like you want, say, let's say input has d features. X belongs to, let's say, r to the power d, right? If x belongs to r to the power d, so what will be your parameters? Your W will belong to r to the power d plus 1 because we add the bias parameter, right? So this nabla will have d plus 1 terms here, right? So whatever each term represents, it's like derivative of like L with respect to each ith parameter of the parameter vector, right? So that will be a single column vector, and that will have these entries. But if you see like L, so this is our kind of this is our loss, right? This is our loss that we want to minimize. So this loss directly doesn't depend on the W. It depends on P and Y. Y is independent of W. Y is constant that is given to us, right? P is dependent on W. Now we'll apply chain rule to kind of get reach the parameter W, right? How do we apply chain rule? So okay, let me rewrite that here again. So what we have, yi log pi then plus 1 minus yi log 1 minus pi, right? So we can ignore these terms completely. Now what we have to do, first partial derivative will be with this term, whatever this is. Let's say here I have taken this as if you will kind of compute this del L by uh, this formulation is, let's say, some loss, right? So this del L by del P first we have to compute. This is the first computation we are doing. Now what is PI? PI we know is sigmoid of W transpose X, right? So now what we will have to do? Now we have to take PI's derivative with respect to this whatever this sigma term is. So this sigma term, let's say I'm representing as Zi, let's say here. Are you getting? So why I'm breaking like this? Because I'm writing Z as double transpose. Sorry, so not this. PI is this. 1 second. PI is this, but this double transpose X I'm writing as Zi. So what I'm doing, I'm computing the partial derivative of PI with respect to Zi. Now Zi is a double transpose X. So that is directly related to W. So now I can compute partial derivative of Zi with W. So that's how the chain rule will unroll. So del L by del Wj or whatever it is. So the superscript represents the index of the parameter, and the subscript here represents the instance number in the input data set. So it's like ith data point, jth parameter, right? So it's like kind of 2D matrix we'll get. Um, yeah, so now if you will do, so what will happen to individual term of the partial derivative, del L by del Pi will be, so if you take this will be yi by Pi, then 1 minus y by 1 minus Pi, this is easy. Now what will be del P by del Z? So what is the derivative of sigmoid? So if you see sigmoid, so where I have space, so if you see sigmoid, what sigmoid of Z or some whatever X it is, 1 by 1 plus e to the power minus Z, right? So if you take the derivative of this, so it will be what it will be, e to the power minus Z by 1 plus e to the power minus Z square, right? Now you add plus 1 here, minus 1 here. So now you can easily kind of simplify this, and it will be sigmoid into 1 minus sigmoid. So that's the derivative of sigmoid. Okay. So this simplification you can do on your own. Right. So that's what we have written here. Derivative of sigmoid will be a sigmoid into 1 minus sigmoid. And then what you have to do, you have to whatever the remaining parameter is only Z. Z you have to take the derivative with respect to W. And what is Z? Z is W transpose Xi, right? W transpose Xi in the sense. So W has W has D plus 1 parameters as we discussed, right? But what we are taking, so if you have to take it little carefully. So we're computing the derivative of Zi with respect to Wj. The Wj meaning we are only concerned about the jth input in the input feature, right? So if we're only concerned about jth input, then with respect to all other input, it will be 0. Partial derivative will be 0. Only leftover term will be xij, right? So now we have to like kind of track backward and put all the values in the respective places in this formulation. So this is 1, this is 2, and this is 3. So now if you multiply these 3 terms, this will the partial derivative will be like this. Now, so there was a point yesterday we discussed. So logistic regression doesn't have a closed form solution. So linear regression we saw closed form solution using calculus and using linear algebra, but logistic regression doesn't have a closed form solution. Why? Because if you see this, whatever the partial derivative we got here, what is happening to the partial derivative? Even after doing the partial derivative, sigmoid is retaining, right? So as sigmoid is retained, so each term is 1 plus e to the power minus w transpose x, right? So into 1 minus 1 by 1 plus e to the minus w transpose x. So given this formulation in one of the steps during backpropagation, during this partial derivative computation, you cannot segregate this w from x. So when we'll get the closed form solution, if we can get like kind of separate this, what is happening? So in the during partial derivative, you have a term sigmoid into 1 minus sigmoid. Sigmoid is 1 by e to the 1 plus e to the minus w transpose x. So for closed form solution, what you need? You need something like w can be written as some function of x comma y, right? So as during partial derivative, this form occurs, you cannot segregate w from x anytime because that's there in the like kind of chain rule multiplication. So it will come continuously. So you cannot segregate w from x. So that's why we're unable to get closed form solution. Right. So only thing we can do is gradient descent, the iterative algorithm. Right. So where are we? So we took the partial derivative of L with respect to Wj. Now, whatever, if you simplify this term, you will get this formulation. So how will you get this formulation? So what you do? So this should be okay. Okay. So all these terms should be capital Pi. Okay. Maybe in the slides I will share. Maybe today's slide there will be this error. I don't have time to edit. So tomorrow I will update the slides. So this all these terms will be capital P as per the like kind of whatever terminology that is used in the previous slide. So what we'll do, so if you kind of do this simplification, it will be pi into 1 minus pi in the denominator. Then you multiply 1 minus pi with yi, pi with 1 minus pi, and p minus p into 1 minus pi will get cancelled here, this and this, and whatever, this will be the leftover thing, right? Now if you kind of open this up, yi, and here it will be yi minus yi into pi. Here plus yi into pi will get minus minus plus yi into pi. These two terms will get cancelled. Only leftover term will be yi minus pi from this simplification, and xij is there, right? So now, so you can represent this to something similar that we discussed last during linear regression. This is x transpose y minus whatever w transpose x we are able to get last time, but here it is sigmoid of w transpose x, right? So every time this w and x, they are staying together, they cannot be separated from each other. So that's why we don't have the closed form solution, right? So this is the complete step for the logistic regression. So once you know this, you can apply whatever your gradient descent step, right? So given like, let's say you are asked to write, I'm not saying whether you will be asked to write the logistic regression code from scratch or not. You will see the question during lab. So if you have to do, so you have to compute everything individually. So this term, this term, this term, you have to compute, then multiply, all these things you have to do. So instead of that, directly you can compute this also, right? So you know you have to write a sigma function, you have to compute this, you have to multiply this, and you started with some hyperparameter. Sorry, let's say some randomly initialized w, like you iterate till you converge to some point. So how do you decide the convergence criteria? So if wt plus 1 minus wt is less than some threshold delta, right? So this is your convergence criteria. Or you if you don't have this convergence criteria, you have convergence criteria like epoch. You can run for some epoch, let's say some 100 epoch or 50 epoch. So that can be your stopping criteria, right? So that's the during training time. During inference time, what you do? So you are given some input data point that has d-dimensional feature. You know the w, right? So you just multiply w transpose x, take the sigmoid and y minus that, and you you take the sigmoid. So during inference, what will have? You have x, that is d-dimensional feature, d cross 1 cross d, uh, let's say d cross 1. Now you have W is D cross 1 also. If you do W transpose X, you will get whatever some real number you will get, right, between minus infinity to infinity. Now what you do, you apply sigma to this W transpose X, you will get something between 0 to 1, right, both inclusive, something between 0 to 1. Now you make decision. If it is greater than 0.5, this belongs to class 1. If it is less than, or let's say greater than equal to 0.5, it belongs to class 1. Less than 0.5, it belongs to class 2. So this is your inference during inference time decision making. Okay, any doubt in the binary? This all about the binary classification scenario, right? So this mathematics little bit messy on the slide it is looking, but whenever I'll share the slides, if you follow, it is very easy. Not a big deal for you guys. Any doubt what you do during inference time? Okay, so this is all about the binary classification scenario for logistic regression. Now we'll see what we have to do for multiclass, right? So for multiclass, yeah. So in binary case, what happened? We had the input X, that is D dimension, 1 cross D again. Sorry, D cross 1. Or, yeah, D cross 1. What you are doing? You are multiplying with a single parameter vector that is giving us a single number, right? Some real number it is we are getting. That we are applying sigmoid or converting into probability between 0 to 1. That's different story, right? In multi-class case, what you have to do, like, so if you see here, to make decision between 0 and 1, we need just a single real number. But let's say you are asked to make decision for 3 classes. Let's say class 0, class 1, class 2. 3 classes are there, right? And we discussed yesterday why applying linear regression to this kind of scenario is not useful, because they don't capture the semantic relation between these different pair of levels, right? So how logistic regression is addressing that? It's kind of getting the probability, like it's converting into some probability distribution, right? So for each class level, we know what is the kind of density, right? So if you know the density, then we can kind of compute, okay, which has highest probability, and we'll get that particular class, right? Kind of it is try to, because it is condensing everything, all the outputs between 0 to 1, and sum has to be, sum of probability will be equal to 1 also. Kind of it tries this condition, particularly this condition of the probability, forces the model to find a relation between these all three class levels, 0 1 1 2 or 0 2, right? uh, so that's how logistic regression is able to address that situation, right? Now in multiclass, how do we do this, right? So in multiclass, what is given to us? We are given k classes, right? But k classes, how do we kind of represent k classes in term in during this linear, logistic regression formulation? We have to convert them into something called one-hot vectors. One-hot vectors. What is one-hot vector? Let's say you are converting 0, 1, 2 into one-hot vector. So how can you convert this into one-hot vector? We know there are three numbers. Three numbers can be represented by a three-dimensional vector. So each can be represented by a three-dimensional vector. So what will be the entries of those vectors? If the level is 0, then 0th entry will be 1, everything else will be 0. If level is 1, then first level will be a 1, everything else will be 0. If level is 2, then second, like in computer science, everything starts from 0. Second index will be a 2, sorry, second index will be 1, everything else will be 0. So that's how we'll convert this given y level into one-hot vectors. So now this is our updated y vector. So this is not just the numbers, not just the single levels representing the y class. So it's like for every y level, we have the corresponding one-hot vectors. Now all these things we know, like we have to get the probability for all the y classes, right? Sorry, k classes, right? this condition will hold definitely. Now how do we do it? So we know this, whatever the probability we are getting, that is able to capture this relation. So each probability of each class will be is somewhere directly proportional to e to the double transpose x, right? So that's what we saw in the binary logistic regression. This relation holds. So now if this holds, like if we are able to convert like project this not project at least assume this relationship holds, whatever the probability of ith class will be, that is directly proportional to e to the double transpose x. Now we can get what the probability will be exactly. So exact probability will be, so that particular term for the ith class over all other k classes, right? E to the power double transpose x for ith class particularly, then and denominator will be e to the double transpose x for all the k classes. So that will give us a probability distribution, right? So if you see, if you like now sum all the terms in this pi vector, it will be equal to 1, because this is a probability distribution, right? So now in a logistic regression, how do we apply this? So what the distribution exactly will be? It will be a multinomial distribution. It's multinomial. It's a multinomial distribution with parameters e to the power double transpose x by s. So what are these s? S is this. This term is s. The denominator here is s, right? Uh, so now here, whatever the loss we saw, this loss, this particular loss, y into log pi or plus 1 minus y into log 1 minus pi, this is something called logistic loss, or log loss, or binary cross entropy loss, binary cross entropy loss, cross entropy loss. Right. So this is by the name of logistic regression. This is a kind of a shorthand notation of the logistic loss. So why this binary cross entropy loss? Binary cross entropy is because of binary classification. What is cross entropy? So for that you have to understand entropy first. I think you guys know, but I'll again discuss today after logistic regression. So then I'll discuss what is cross entropy, right? So what cross entropy tries to do, like on high level, it's try to, so we saw this KL divergence between true and output, right? True distribution and output distribution. So this is something called the cross entropy, right? So if you want to compute uh, entropy, so what is entropy generally? So entropy is, let me tell you here, entropy. Entropy is minus pi log pi. Like, so entropy you compute for a single distribution. So what does entropy signify? We'll discuss now. So what is cross entropy? If you see cross entropy, so it is summation of qi log pi. Log pi. So what is qi? Qi is the true distribution. Pi is the corresponding predicted distribution, right? So again, why we need all these things? So we'll see in the decision tree formulation. So what is the significance of entropy and what is the significance of cross entropy? Okay, so now if you see like how what we are doing in the binary logistic regression, so we are doing something called binary cross entropy. In a multi-class logistic regression, we come from a binary cross entropy to just cross entropy, right? So it's no more binary, just the cross entropy. In cross entropy, what you need? So you need a kind of true distribution and you need a predicted distribution, right? This is what we have to compute in the cross entropy, right? So what will be our true distribution here? True distribution will be whatever the y given to us, and predicted distribution will be whatever the corresponding probability we are getting for that particular y, right? And now we have multi-class scenario. So we are not only this is in not W. So it's not only over all the data points, it's also over the all classes. So you have to like kind of find the optimal W, not only for the data points or for all, but also for the classes. So that's why this argument formulation has another summation term, right? Now, if you kind of vectorize this formulation, so vectorized formulation will be exactly same what we saw in the binary logistic regression, but so dimensions will change now. So x, anyway, x dimension doesn't change. It's let's say d cross n if there are n data points. Then so what will be our y? So y originally is a kind of n cross 1. Originally it's n cross 1 now, but one not encoding, after doing one not encoding, so it will be so n data points and how many classes? K classes, n cross k, if we have k class scenario, right? Or yeah, maybe you can write this in a way, k cross n, k cross n, right? Each column represents its data points, and each column vector represents the one not vector for the k classes, right? That will be y. Then what will be our w? So w, as we know, we multiply here w transpose x, but our output should be of this dimension, right? K cross n. So what will be our w? Into w, you can see it should be also k cross n. So what k cross n w represents? So if we had originally in binary logistic regression, we had only single w vector, right? So that has d parameter or d plus one parameter depending on the bias term. Now what it says? Now we have a what we have? We have kW's, right? So this will be, so kW's will be represented, let's say, like this. This is k cross n, right? So what this kW's tell us? For the first row, when you multiply with the first column of this x, or like all the columns of the x particularly, not a first column, so it will tell for first particular class in the y, right? First particular class in the y, what are the weights, right? So what are the weights for each data point, right? So this dimension, be careful about while doing today's class. So your as I'm saying, this is on linear regression, logistic regression. This will cover all the concepts we have discussed. So this dimension you have to be very careful. So what will be the dimension of w? What will be the dimension f in the multi-class scenario? In binary, it is very easy, right? So any doubt here in particularly this formulation for the multi-class? How did we reach here? And this is also called softmax regression. Softmax regression. Why it is called softmax regression? Because we are using this multinomial distribution. This is called softmax distribution also. And this loss is whatever this we are using. This is softmax to get the probability of the each particular input data point for a particular class level y. Any doubt? Okay, so this is all about your linear regression and logistic regression. So one point I just mentioned during the initial class of the linear regression. So whatever the logistic is a least square estimation method we use. Sorry, let me write completely least square. So I said this is ordinary least square, right? So why it is ordinary least square, I have not told you yet. So when it comes to logistic regression, we are able to do binary classification. Also, we are able to do multi-class classification. Similarly, in linear regression, so whatever linear regression you say, or least square regression you say, whatever the term. So in linear regression, what we discussed, we only discussed predicting a single regressed vector from whatever the input x. So that's why it is called ordinary, because this the y is only one vector, only one vector for ordinary least square regression. If this y is also multiple, so you are trying to so the y vector has multiple regressed points, like it's like you want to regress y1, you want to regress y2 up to yk using same data point x, then it will be a called multi-output least square regression. Okay, it's called multi-output least square regression. Right, same thing, similar to whatever thing we did in the multi-class logistic regression. The formulation in the multi-class multi-output linear regression will be exactly same whatever we saw in the linear regression. You can get the closed form solution also. Only thing will be the dimension of w will change because you have the dimension of y is different also, right? So you the whatever the w vector will get, you will get for each particular y vectors, right? That's the only change you will have. Right, so these are that's another variation of the linear regression, and we saw another variation that is ridge regression. Something similar you can explore, that is called lasso regression. Right, in lasso regression, whatever the map distribution when we did in so what we discussed is ridge regression. So when we did the map estimation, the whatever the regularization term was giving us, that is L2 norm. In lasso regression, the regularization you will get will be the L1 norm of the W when you do the map estimation. Okay, so lasso regression is generally used when you have very sparse data to kind of you have to remove so many features, because many features are very redundant to make some decisions. So you would use lasso regression. If you don't have very sparse features but you want to constrain and get rid of get the impact of outlier minimized, then there you use ridge regression. Right, so these are just some other variants, important variants I want you to know. Others, anyway, when you go for higher classes, you will know what are the different variations of the linear regression and logistic regression. Okay, so that's all about linear regression, logistic regression. Let's quickly discuss the decision. Okay, now coming to decision tree. So what we discussed in last class, something called parameter estimation method, right? Parameter estimation method. So what parameter estimation was giving us? Some parameter w that can be applied to x. Like, so what this parameter w does to x, it transforms x to some space, right? So when you do this matrix vector multiplications, it's just the linear transformations. So it transforms and it makes some decisions, right? You get some decision from this transformation. How do you get some decision? It depends on different algorithms, right? So this is constant across all the machine learning algorithms when parameter is involved, even if it is neural network. So you just multiply some parameters to the input x. Then how do you get this y label? That depends on the task, whether you have a regression task, whether you have a classification task, whether you are doing logistic regression or SVM, all those things changes. This is constant, but this formulation requires a parameter. But there are class of machine learning algorithms that don't require parameters. Don't require parameters. So if you don't require parameters, then the question of backpropagation, all this loss computation, that is completely insignificant, right? So there, the algorithms may not be very optimal, but uh, there are some types of data points for which this non-parametric, so they're called non-parametric algorithms, non-parametric algorithms. Right, so non-parametric algorithms for some kinds of data points, they are very optimal, right? They're kind of trying to learn these w's are not very significant. And also if when you go to non-parametric algorithms, one major advantage we get is they're interpretable because there is no parameter involved. So we only make decision based on the input data point. So we can interpret okay, what is the nature of the data point based on which we are making some decision. When parameters are involved, the parameters are in high dimension, they're black box. We cannot see them in high dimension, but at least we can see the input features, right? So that's why non-parametric algorithms are interpretable. So only one algorithm under non-parametric we'll discuss is decision tree, right? So there are other algorithms. One is, let's say, k nearest neighbor or decision tree regression. All these things we'll only discuss decision tree for classification. So you can explore all these things. Okay. So in decision tree classification, so what you have to do, again, I don't think I have enough time to complete the decision tree. Next week, if I'll get a, I'll get some time to take a part of a class or full class, then I'll complete this decision tree. So what decision tree tries to do, so there is some y level, right? So this is our classification task. So there is some y level definitely. This is our y, and this is our complete x, right? So from this x, we have to predict y. So, and we know there is no parameter involved. So we have to make some decision based on this x. So if you see, if my gold y is like if India wins or not, India wins or not. If India wins, I will say this is one. If not, India loses, it is 0, right? If I am saying this is the scenario for my, like that's the task at hand. So I have to see where the which data points where India has won the matches, and we have to see which features that has helped India to win the matches, right? So if we can kind of find a kind of sweet spot in terms of combination of features, okay, this feature with this value or this set of value, if we'll get, then y will be this, right? So that's what we want to achieve during this using decision tree. Okay, we know this is some y level we want to predict, and for the y level we want to find the kind of best combination of x, like kind of feature values. Okay, if this feature has this value or this feature ranges between this to this, then y will be this, right? So that's the goal of decision tree. So for understanding decision tree, we have to know something called entropy, right? So let's see what entropy is first, then we'll go to the details of the decision tree. What entropy tells, let's say this is a scenario where we're given some balls and they are in like kind of 3 buckets. So given this, like if you see this bucket, you know the color of the balls are white, like always, like this is fixed. Given this box, you know the color of balls are red, right? But given given this bucket, if you want to, if you will be asked like, okay, you pick one ball randomly, what will be the color of the ball? It's not clearly decisible, right? It can be red or it can be white, right? So this are something called undecidability, right? So this undecidability is called entropy. If something is highly undecidable, that is high entropy scenario, right? So entropy is like how how much you are getting kind of perplexed. Like if you saw some distribution, you are unable to make some decision. Okay, you saw some data, you are unable to make this some decision. Okay, this data is definitely for one class or other class, right? So that's the definition of the entropy is, right? For this, like these two buckets, like this bucket and this bucket, entropy will be 0, but there will be some non-zero entropy for this bucket. So how mathematically we define entropy? Okay, so that part is not written here. So entropy is, I think I had it written. Yeah, so this is the formulation of the entropy. So how do we define entropy? So entropy we always define over a random variable, right? So it is like probability of random, like probability of that random variable happening into log of that probability. So that's the entropy, right? So why this is why it is defined like this? Because it is achieving our goal. Like if we know concretely what is the decision, it entropy should be 0. So will see by doing kind of again derivative. When we know concretely the decision, the entropy, whatever this formulation, will boil down to 0. If we don't know, it will be the highest value. So how can we do that? Again, we take help from Bernoulli distribution. Let's say X comes from Bernoulli P. So we know if it is coming from Bernoulli P, probability of happening x equal to 1 is P and x equal to 0 is 1 minus P. And now if you kind of, so there is a minus from here. So put the values, corresponding values in this formulation of the entropy. We'll see why this formulation is correct. So if you put this, okay, so it's somehow hidden. This image would have been on the right side. Okay, so this is the formulation of our, like when you put the values of probabilities in the formulation, you will get this, right? So now if you kind of try to simplify, it is P into log 1 minus P, summation of minus over I. This is P into log 1 minus P. So now what you have to do, you have to kind of find this parameter. What will be the parameter when uh, so our goal is get the P value for which this particular term, this hx is maximized, hx is maximum, right? Because so entropy, when what we can, or you can do the minimum also. What we are saying, entropy by definition it can be minimum 1 or maximum, sorry, minimum 0 or maximum 1, right? So that's what we want to achieve. So this in the slides it will be this will not be here, so I'll shift it. So what it will give us, this is P into log 1 minus sorry P into log P plus 1 minus P into log P, log 1 minus P, right? Now if you kind of take the derivative of h with respect to P, you will get minus P by P. So there is a minus term here, minus P by P. Then minus log P plus log 1 minus P. So now if you kind of simplify this, you will get P equal to half. So if P equal to half, what it says, let's say you have like kind of two types of data points in a bucket. If all the, like both the types have equally distributed, then only the entropy will be highest. That is the one, right? So what will be the plot of the entropy if you try to see? So it will be like this. When the p value is kind of the in midway, midway half, this is highest. Then when p values are close to 0 or 1, this is the lowest. Right? This y-axis tells the entropy. This y-axis is entropy, right? So this is for the binary case. Similarly, if you see for the multi-class case, if the distribution is uniform, like if you have the given distribution is uniform, the entropy will be always highest. So that's intuitively also by definition we can say, if entropy, sorry, the distribution is uniform, we cannot make any concrete decision, then the kind of the entropy will be highest. So this is every class I mentioned one of the problems for the potential for the exam. This is one of the problems that is potential for the exam. For uniform distribution, if x is coming from the uniform distribution, with some parameters a, b, then it has highest entropy. Okay, so maybe you are asked to solve this during exam. Okay, so this is where maybe we'll stop today. So then we'll see how do we use this entropy formulation to find which combination of features will give us the correct y level. Okay, so that will be the next class of the day. Okay, so be careful if you are asked for this multi-class logistic regression, you have to convert the input data into, sorry, y level into this one odd vectors, then do the formulation. Okay, so this is something very crucial.